Hello everyone, my name is Xiaomin Zhou from Huazhong University of Science and Technology. Today I will introduce our work, ROWE-tree, a read-optimized and write-efficient B+ tree for persistent memory. My talk consists of 4 parts. The first part is background and motivation. We then present our work, ROWE-tree. The last parts are performance evaluation and conclusion. Emergency persistent memory provides persistence, high capacity, lower price, fast adjustability, low latency, and low standby power. These features make PM very attractive to complement or replace DRAM as main memory. Persistent memory shows a huge potential to provide indexing structures with high performance, efficient persistence, and instant recovery. B+ tree is a fundamental building block in storage systems. In the past 10 years, a large number of research has been proposed to improve B+ tree indexes for PM. However, most of them fail to provide high performance for both read and write operations. We conclude 2 reasons that account for such an issue from the perspective of software and hardware. First, from a software perspective, the read and write designs of existing persistent B+ trees restrict each other. In traditional B+ trees, all items in a leaf node are sorted so that they can obtain good read performance by binary search. But keeping leaf nodes sorted will reduce write performance, since it causes multiple PM writes and high consistent guarantee overhead. To reduce sorting overhead, some research propose unsorted leaf nodes, but this way needs to scan the nodes to find the key item, and thus slow down the search speed. To accelerate the search in the unsorted leaf nodes, previous work introduced additional metadata, for example, fingerprints or throw areas to avoid scanning the entire leaf node. Unfortunately, it also leads to additional metadata overhead. To solve this problem, our B+ tree leverages entry-moving to bench the persistence of metadata and items, but the metadata overhead still cannot be dismissed completely. As a result, most existing work fails to offer high performance for both write and read operations. Second, from a hardware perspective, PM suffers from a serious read and write interference problem, and this interference becomes more serious as the number of threads increases. As the slide shows, the bandwidth of 18 read threads is 13.7 GB per second. When adding 6 read threads, the read bandwidth reduced by 18 GB per second. Similarly, the bandwidth of 6 write threads is 13 GB per second, and decreases up to 7 GB per second when running with 18 read threads. However, existing PM B+ trees overlook the read and write interference problem on PM. As we know, real-world applications often have hotspot issue, that is, most accesses only touch a small portion of items. We measure the access ratio of hot items in simulated production workloads, which are generated by YCSB. This slide shows the results. We see that the 160,000 hottest items can receive at least 50% of accesses. Inspired by the hotspot issue of real-world workloads, we designed our ROWE-tree that migrates accesses to hot items to DRAM. to reduce the read and write interference problems on PM. To this end, we have proposed the scheme ROWE-tree, a read-optimized and write-efficient B+tree for PM. We aim to improve both read and write performance. As the slide shows, ROWE-tree contains two main parts: a write-efficient B+tree, WE-tree, and a read-optimized table, RO-table. The WE-tree is used to keep items durable and mainly serves write operations. The RO-table is stored in DRAM and absorbs accesses to hot items to relieve the load on the WE-tree. The WE-tree stores non-leaf nodes in DRAM and stores leaf nodes in PM. Since non-leaf nodes of a B+trees are read frequently, while leaf nodes are written frequently. By doing so, we can alleviate the read and write interference on PM and improve write performance. The WE-tree supports optimistic concurrence control like B-link tree. It combines self-verifying insertion mechanism and semi-sorted leaf nodes to improve performance. We now describe the self-verifying insertion mechanism. The item is inserted in an appended way, but we leverage its key as the persistent mark instead of additional metadata, for example, bitmap. Since modern processors support 8-byte atomic write natively, we split the key into two parts: the 8-byte persist key and the remaining key. The split principle is to separate the critical 8-byte key to make remaining key smaller than the smallest key of the leaf load. Next, we first write remaining key and the value, then store persist key as the persist mark. This ordering guarantees that persist key is written after all the other parts of the item have been written. If system crashes, we can identify partially written items because the remaining key is invalid. These mechanisms can reduce the persistent overhead. For example, as the slide shows, previous work first persist the key V12 and then persist the bitmap, which needs two persistent instructions. The self-verifying insertion only requires one persistent instruction to persist key V12. Therefore, our self-verifying insertion mechanisms can significantly improve write performance. We then design semi-sorted leaf nodes that keep items in a cache line sorted. This way can reduce unnecessary key comparisons and improve read performance. For example, when the saturated key is 4, for unsorted leaf nodes, we need to find the 6 rows. But for semi-sorted leaf nodes, we only need to search 2 rows. In the meanwhile, the additional writes caused by cache line sorting do not reduce write performance, since the number of modified words in a cache line does not impact the PM write performance. The RO-table is a DRAM cache of hot items that migrate accesses to hot items to DRAM, thus reducing the read and write interference of the WE-tree. The structure of our table has 3 steps. First, we use 3 schemes to improve space utilization. Every bucket is set with multiple rows to store conflicting items and allows insert operations to probe both the target bucket and the flowing bucket. If there is still no empty slot in the 2 buckets, we insert the item to overflow buckets. Second, we use fingerprinting to filter unnecessary PM reads, which can optimize the read performance. Third, we use an optimistic locking mechanism to obtain good scalability. In real applications, the hot items are changing during running time. We use a lightweight hot items identification and replacement. We set a weight for each item of the R table by using its access count. And to minimize interference induced by the weight update and the hot items replacement, we use a periodical sampling method. After every R operation, we update the weight of the target item or replace crowd item in the R table. Now we show the experiments and analyze the performance of our ROWE-tree in this part. All evaluations are running the systems with inter-option DC persistent memory. The benchmarks are YCSB workloads. We compare the ROWE-tree with other related works. Node size is a key factor that impacts the performance of the B+ tree. In the first experiment, we test the impact of different node size on the performance of the ROWE-tree. The slide shows the results. According to the experimental results, we set the non-leaf nodes to 384 bytes and set the leaf nodes to 256 bytes for the rest of the experiments. Second, we compare our ROWE-tree with other PM-B+ trees. Experimental results report that our ROWE-tree has the best performance. It can reduce the insertion latency by 27%, 42%, 30% than our B+ tree, pass and fail, and tips. For search operations, our ROWE-tree can reduce search latency by 44%, 56%, 61% than our B+ tree, pass and fail, and tips. Third, we use 4 YCSB workloads to evaluate the scalability under an increasing number of threads, getting benefits from self-verifying insertion mechanism and the R table. Our ROWE-tree offers higher scalability and performs better than our B+ tree, pass and fail tips by 2.6, 3.8 times. Finally, we set a sensitivity analysis of our ROWE-tree considering the R table size and the skewness of workloads. As shown in this slide, the left figure shows the throughput under different R table size. We see that the throughput of our ROWE-tree grows by 1.13 times with increasing the R table size. The right figure shows the throughput under workloads with different skewness. We observed that with the growth of skewness, the search performance of our ROWE-tree significantly improves and achieves up to 1.9 times speed up. In this paper, we analyzed the existing PM-based B+ trees. We find that their read and write designs restrict each other and overlook the read and write interference problem on PM. As a result, these works cannot offer higher performance for both read and write operations. We propose our ROWE-tree, a read-optimized and write-efficient B+ tree for persistent memory. Our ROWE-tree consists of ROWE-tree and R table. The ROWE-tree designs a self-verifying insertion mechanism to reduce persistent overhead, and the semi-sorted leaf nodes to speed up the search. To alleviate the read and write interference problem of PM, we introduce a DRAM R table to migrate access to hot items to DRAM, and then use a lightweight hot items identification and replacement to cope with the changes of hot items. The experimental results shows that our ROWE-tree has better performance and higher scalability than the state-of-the-art work. That's all. Thanks for listening.